Welcome to Technophilia, a show where we bring you the top stories from the world of science and technology. So let's discover what's concocting there. Nature holds within itself a diverse range of systems that are for us to learn about and benefit from. These systems have been of particular interest, especially to scientists in the field of robotics. Be it learning from the workings of the brain to develop AI or from squirrels to incorporate their parkour abilities into the robots, scientists have adapted much from nature into their technologies. In this regard, physicists at the University of Bath are working on the next generation of robots, which they say will be shapeshifters. For this, they have developed a new way to coat soft robots in materials that allow them to move and function in a more purposeful way. The authors of the study believe their breakthrough modeling on active matter could mark a turning point in the design of robots. With further development of the concept, it may be possible to determine the shape, movement, and behavior of a soft solid, not by its natural elasticity but by human-controlled activity on its surface. The surface of an ordinary soft material always shrinks into a sphere. Think of the way water beads into droplets. The beading occurs because the surface of liquids and other soft material naturally contracts into the smallest surface area possible, a sphere. But active matter can be designed to work against this tendency. An example of this in action would be a rubber ball that's wrapped in a layer of nanorobots, where the robots are programmed to work in unison to distort the ball into a new predetermined shape, say a star. It is hoped that active matter will lead to a new generation of machines whose function will come from the bottom up. So instead of being governed by a central controller, the way today's robotic arms are controlled in factories, these new machines would be made from many individual active units that cooperate to determine the machine's movement and function. This is akin to the workings of our own biological tissues, such as the fibers in the heart muscle. Using this idea, scientists could design soft machines with arms made of flexible materials, powered by robots embedded in their surfaces. They could also tailor the size and shape of drug delivery capsules by coating the surface of nanoparticles in a responsive, active material. This in turn could have a dramatic effect on how a drug interacts with cells in the body. Work on active matter challenges the assumption that the energetic cost of the surface of a liquid or soft solid must always be positive, because a certain amount of energy is always necessary to create a surface. The first author of the study say active matter makes us look at the familiar rules of nature, rules like the fact that surface tension has to be positive, in a new light. Seeing what happens if we break these rules and how we can harness the results is an exciting place to be doing research. Corresponding author added, this study is an important proof of concept and has many useful implications. For instance, future technology could produce soft robots that are far squishier and better at picking up and manipulating delicate materials. For the study, the researchers developed theory and simulations that described a 3D soft solid whose experiences activate stresses. They found that these active stresses expand the surface of the material, pulling the solid underneath along with it and causing a global shape change. The researchers found that the precise shape adopted by the solid could then be tailored by altering the elastic properties of the material. In the next phase of this work, which has already begun, the researchers will apply this general principle to design specific robots, such as soft arms or self-swimming materials. They will also look at collective behavior. For example, what happens when you have many active solids all packed together. Meanwhile, a team of scientists at the Max Planck Institute for Intelligent Systems and the University of California, Irvine have constructed a robot leg called BirdBot that, like its natural model, is very energy efficient. For scientists, flightless birds like the ostrich have been a mechanical wonder. Ostriches, some of which weigh over 100 kg, run through the savanna at up to 55 km per hour, which is attributed to its leg structure. Unlike humans, birds fold their feet back when pulling their legs up towards their bodies. But what is the function of this motion? Well, this team attributes this movement to a mechanical coupling. The lead scientist states, "We hypothesized a new function of the foot-leg coupling through a network of muscles and tendons that extends across multiple joints. These multi-joint muscle tendon coordinate foot folding in the swing phase. In our robot, we have implemented the coupled mechanics in the leg and foot, which enables energy-efficient and robust robot walking. The coupling of the leg and foot joints and the forces and movements involved could be the reason why a large animal like an ostrich can not only run fast but also stand without tiring," the researchers speculate. A person weighing over 100 kg can also stand well and for a long time, but only with the knees locked in an extended position. If the person were to squat slightly, it becomes strenuous after a few minutes. The bird, however, does not seem to mind its bent leg structure. Many birds even stand upright while sleeping. A robotic bird's leg should be able to do the same. No motor power should be needed to keep the structure standing upright. To test their hypothesis, the researchers built a robotic leg modeled after the leg of a flightless bird. They constructed their artificial bird leg so that its foot features no motor, but instead a joint equipped with a spring and cable mechanism. The foot is mechanically coupled to the rest of the leg's joints through cables and pulleys. Each leg contains only two motors: the hip joint's motor, which swings the leg back and forth, and a small motor that flexes the knee joint to pull the leg up. After assembly, the researchers walked BirdBot on a treadmill to observe the robot's foot folding and unfolding. They found that the foot and leg joints don't need actuation in the stance phase. Springs power these joints, and the multi-joint spring tendon mechanism coordinates joint movements. When standing, the leg expends zero energy. Previously, our robots had to work against the spring or with a motor either when standing or when pulling the leg up. To prevent the leg from colliding with the ground during leg swing, this energy input is not necessary in BirdBot's legs. Overall, the new robot requires a mere quarter of the energy of its predecessor. The treadmill is now switched back on. The robot starts running, and with each leg swing, the foot disengages the leg spring. To disengage, the large foot movement slacks the cable, and the remaining leg joints swing loosely. This transition of states between standing and leg swing is provided in most robots by a motor at the joint, and a sensor sends a signal to a controller, which turns the robot's motors on and off. Another scientist from the team links the bird's remarkable locomotion robustness to a morphological intelligence that is built into the system that allows the animal to act quickly without having to think about it. Her work on running birds over 20 years demonstrates that birds respond more rapidly than the nervous system allows, indicating mechanical contributions to control. If I assume that everything in the bird is based on sensing and action, and the animal steps onto an unexpected obstacle, the animal might not be able to react quickly enough. Perception and sensing, even the transmission of the stimuli and the reaction cost time, she says. Now that the team developed BirdBot, it all makes more sense. The leg switches mechanically if there is a bump in the ground. The switch happens immediately and without time delay. Whether it's on the scale of a T-Rex or a small quail or a small or large robotic leg, theoretically meter-high legs can now be implemented to carry robots with a weight of several tons that walk around with little power input. But is everything going smooth in the world of AI, or are there any challenges? And what are the dangers of using AI in some fields? We'll leave that for the next video. Until then, do give us your thoughts about these robotics discoveries in the comments.